Welcome bio student viewers. This screencast will describe the following: a chemical reactions overview, what are catalysts, and biological catalysts, which are enzymes. First, let's take a look at chemical reactions. Chemical reactions consist of a change in a substance to a new one. Easy enough. Here we see many examples of chemical reactions. Look for the evidence in each example. Things like a color change in the liquid or the gas, an emission of light, production of heat, change in the state of matter, like liquid to gas or liquid to solid, and vice versa. In each case, we start with reactants. After the reaction, we have products. These are the new substances with a new chemical makeup different from the reactants or the starting substance. So let's take a simple reaction as an example to demonstrate chemical reactions. Generally, any reaction consists of two parts: reactants, or sometimes called the substrates. These are the starting materials of the reaction. In this case, our starting material is hydrogen peroxide. And the products, these are the ending materials after the reaction is completed. Here our products are water and oxygen, and the arrow next to the oxygen symbol indicates that oxygen is released as a gas. You might recognize hydrogen peroxide in wound healing. Hydrogen peroxide is a chemical similar to water. Water has the chemical formula H2O, while hydrogen peroxide is H2O2. Under the right conditions, hydrogen peroxide breaks down into water and oxygen gas. The oxygen is what makes the bubbles. This substance is put in dark bottles to slow down the natural decomposition of the hydrogen peroxide to water. In hospitals, hydrogen peroxide is thrown out after about 2 or 3 months. Even a simple reaction like the one we see here, hydrogen peroxide goes to water and oxygen gas, needs energy to start the reaction. This energy will break and/or form chemical bonds. The energy required to start a reaction is a special kind called the activation energy, or E sub A. The energy barrier makes the reactants unstable and more likely to form products. In most reactions, the activation energy is some application of heat. This wouldn't be true for biological organisms, but we'll talk about that next. Without this activation energy, E sub A, reactions would occur spontaneously and without control. We can think of E sub A as the amount of energy needed for a reactant to move uphill to a higher energy but an unstable state, so that the downhill part of the reaction can begin. One way to speed up this reaction, as I said, is to add heat. Heat is going to increase the movement in the matter, agitate the atoms so that the bonds break more easily, and the reaction can proceed to product. That's making the reactant unstable. But another way is to add a catalyst. So let's take the same reaction that we've been using. Hydrogen peroxide goes to water and oxygen gas, but add a catalyst called potassium iodide. And add a little dish soap so we can see the reaction. Let's watch the next couple of Steve Spangler, the science guy, with Ellen to show this catalytic reaction of hydrogen peroxide to water and oxygen gas.
All right, so here, this is kind of fun. So when you got a cut as a kid, you would always put on, well, Mom would always put hydrogen peroxide on, you know, that stuff.
I wish they would have done that for me.
So this is just like really concentrated hydrogen peroxide, and it's got a little dye in there in the bottom, so this should be perfect, all right?
All right.
You really only need about 3 drops, but I was thinking for a big show, why not, all right? So here, this is your part. You squeeze in some soap.
Okay.
Right? So put in
How
some
much?
soap. Just Oops, that's too much.
Okay.
All right, so, no, it's fine. Just a little bit more is good.
Okay.
Okay, good. And now let's squirt a little bit in this one here. We're set? Okay, good. That's perfect.
All
now,
right.
this, over time, the reason why people keep, that hydrogen peroxide in the refrigerator is to keep the oxygen from coming out.
Okay.
So this stuff right here actually makes it come out really, really fast. All right, so this is this catalyst that's kind of fun. So when we pour this in here, my only suggestion to you is that, no, God, no. That's bad. Man, that was really bad.
I see something in a shot glass.
No,
like
that's...
What do you do?
No, that's not a shot glass.
Okay.
That's a
All
very
right.
scientific beaker.
I was going to put it on my belly button. I was going to have you. All right, what do we do?
All right, so now, when I say go, you pour it in there and then stand back. Fast. All right? Ready? Here we go. 3, 2, 1, dump it in and stand back if I were you.
Wow.
Is that cool? Now I just can't get it to stop. All right, it just keeps going.
Wow.
That's fun.
That's amazing.
Pretty cool stuff, hey? But the science here is pretty straightforward. Potassium iodide is acting as a catalyst for this reaction. Catalysts are things that are going to speed up the rate of reaction by reducing the amount of activation energy needed for the reaction. The other characteristic is that they don't become a part of the products of the reaction. That is, in this case, potassium iodine wouldn't combine with water or oxygen to make some different product. It stays uniquely itself. So in the graph here we see energy needed for a reaction to go to product, uncatalyzed versus catalyzed. And the difference is the amount of energy needed to go to products. And that's what a catalyst does, is it reduces that amount of energy for the reaction. So what's the relationship between catalysts and biological organisms? Well, in biological organisms, reactions must occur rapidly to keep up with metabolism of the organism and also occur without a temperature change in the organism. They have to occur with less activation energy so that the reaction can go to products without much input of energy. So in this sample, the student is using liver tissue. It's a biological tissue. She's ground it down quite a bit so that would break up the cells. And now she's going to place the hydrogen peroxide into the test tube with the liver tissue. And we can see the evidence for the reaction here, which is the formation of a gas. So the liver tissue must contain the catalyst that is promoting the reaction of hydrogen peroxide to water and oxygen gas. In liver cells, the enzyme catalase works as the catalyst in the reaction that decomposes hydrogen peroxide to water and oxygen gas. Catalase is a protein. It's found in the cell. It operates as an enzyme. And enzymes function as biological catalysts by lowering the activation energy needed for a reaction to begin. They also will increase the rate of the reaction without being consumed up and are usually proteins, although some RNA molecules can function as enzymes. Let's see how enzymes work with this McGraw-Hill video, and then I'll see you in the next screencast. Ta-ta for now. Take care.
Enzymes are proteins that speed up chemical reactions in the cell. A special region on the enzyme, called the active site, has a shape that fits with specific substrate molecules. An enzyme works by binding to one or more specific molecules called reactants or substrates. Binding occurs at the active site. The enzyme and substrates form an enzyme-substrate complex. The interactions between the substrates and the enzyme stresses or weakens some of the chemical bonds in the substrates. These stresses encourage a link between the two substrates, leading to the formation of a different molecule. As a result of the chemical interactions within the active site, a new product is formed. The product is released from the active site. The enzyme assumes its original shape and is free to work again. Although this reaction has specifically illustrated the formation of a single product from two substrate molecules, other enzymes catalyze the formation of two products from a single substrate.